We will now talk about Gurobi Compute Server, Cloud, and Distributed Optimization. So we'll start out with the basic ideas, the foundation, which will be Gurobi Compute Server. And then the step 2, we'll talk about optimization using the cloud. So putting Gurobi Compute Server onto the cloud and running on a cloud computing environment. And then once we've got those ideas in mind, we'll talk about a killer app for Gurobi Cloud to use Gurobi distributed optimization algorithms. So let's start with the basic ideas in Gurobi Compute Server. So if you are been doing optimization for a long time, you're probably familiar and building your optimization applications with a sort of standard system architecture. On the left-hand side of the slide, you see a single computer where both the Gurobi interfaces, the APIs, and the algorithms, they run together on a single computer. With Gurobi Compute Server, we can separate that out and put those onto 2 separate computers. So we'll do remote computation where we have a client computer where only the Gurobi interfaces, the APIs will run, and then a second computer where the optimization algorithms will run on a server. So those 2 will be linked, and we'll separate those 2 out, which is a little different than what you're probably used to, where they all run on the same computer. And once you separate those 2 things, you could do some very interesting things. You could have multiple clients connect. You could also have them connect not just to one computer, but to connect to multiple computers. This allows us to do things like queuing and load balancing. So the Gurobi Compute Server seamlessly offloads the optimization jobs to 1 or more servers. And so you could get access to powerful machines. Like, let's say you have a laptop, but you want to do the computation on a very powerful server. That's very easy to do with Gurobi Compute Server. You could also share resources across users, teams, and applications. So you can use a Gurobi Compute Server that works with multiple users or multiple applications. You could do high availability by having multiple compute servers run together, and if any one of them fails for some reason, the application can still run. And then you can also build some modern architectures where you separate the different parts of your application into different computers. So the best way to understand this is to look at the demonstration. So I'll try to show you a simple demonstration of this. So I'm going to run 2 different windows. Let me make the second window a little larger. And so on one window, I'm going to log into a computer and start the Gurobi Compute Server. So let me do that first. And I'm going to give it a few parameters. I'm going to say the port is going to be equal to 8080, and I need to give the host name, and that one is going to be called i60.compute.gurobi.com. And that should start right now. That looks okay. So that on the top left window, you see the compute server is running, and on my bottom right window, I'll run as a client. So I could run, say, Gurobi CL, and then I'll say my server equals, I'll put the same info from that other window, i60.compute.gurobi.com, port 8080, and then I'll solve a little model. Let's take, so I'll solve a simple linear program, and it worked. And that way, that's a very simple model that runs quickly, but let's take a look at some of the information. It says it has a job ID, and there was capacity on my server, it connected. And this time, because it's a server that runs on the Gurobi network, I'm not bothering with encryption, I'm just doing a very simple connection. So it told me this is an unencrypted connection. And then it solved this simple linear programming model. And at the end, it told me how much time was spent in the communication, as well as the usual log information. It tells me the computation information. And on the server side, I could see that when I ran that model, there was some information that it started to solve, what kind of model it was, and what was the model size, that was finished, and that it was finished. So I could solve an integer program as well, like P0033 MPS. So this time it'll solve an integer programming problem, and the same idea is that it runs on that remote server. And if I go back to my log, I can look back. I see all the usual log information plus the information telling me that it's running on that remote server. So if I did that same solve on my local computer, it would look mostly the same. So I didn't have to change anything except to remove the remote computing string, and I could just solve that same model on my local computer, and it runs just the same way. So it really looks and operates just like I'm running locally, but it's running on a nice remote compute server. And it was very easy to set up. Now that's of course running in an interactive mode. Of course, there's other ways to run the server. Let's go back to the slides and let's look at some of the details behind the scenes. So in version 8, we improved the architecture for Gurobi Compute Server in a number of ways. One of which is that we changed to use standard web technologies. In the old versions of Gurobi Compute Server, it was a proprietary protocol. And this was, while it was effective, it had a lot of downsides for communications and for working on corporate firewall technologies. Now we're using standard web technologies. We could use, it basically works on the same principles as a web page. And so you can use standard HTTP or optionally secured HTTPS, which makes it work much better with corporate firewalls and proxy servers. And it's also, while it's using security, and the old version had security as well as the new, now the security is using web standard technologies. It also has much better robustness to handle intermittent network issues. Since I'm working from my home office, if there was some problem with my internet connection that caused a short glitch, it would still work. The older version, if there was any kind of short glitch in my network connection, like with a wireless Wi-Fi connection or with a home internet connection, it would have stopped the whole solve. And so now it's much more robust. Also in version 8, we've got new clustering capabilities. I didn't demonstrate that here, but I will in a little bit when we go to the cloud. You can add nodes and allow them to join or leave the cluster much more easily. The job balancing would then work to, if I had multiple clients connecting, it would load balance that among different nodes. And then the client will connect to whatever node has the best availability. So to set up a cluster, we did change some of the packaging. So if you're using Gurobi Compute Server, on the server side, it's a separate download. So you just download the Gurobi server components and install that on the server. It's a separate download, a separate installer, and it has its own separate reference manual. So you could give that to your system administrator and say, read this. They don't have to be an expert in optimization. They just have to read the basic configuration instructions for the Gurobi remote services. You've got a couple of different ways to configure it. I use the command line configuration, but in more robust applications, you're probably going to configure it through a configuration file. That way it'll be persistent. You don't have to remember those configuration parameters. It's also got to have configuration parameters to do the secure configuration, what port you're going to run in. I ran on port 8080, so I didn't need root privileges. There's also help information. And it's very easy to start it. I ran it interactively. You can also run it as a service, as shown here in the bottom of this slide. There's commands for managing the cluster. That's when you're running multiple compute servers, and that works with the new GRB cluster command, and that lets you do administration of the cluster remotely. What I did was I just solved a very simple job using the Gurobi optimizer on my remote computer, and I just specified the server. And here in this slide we say server equals server 1, and I solved a model. And also run the cluster command to see the status of my nodes. Here in this slide, I've got multiple nodes. In my demonstration, I just had one. And we can also see the status of any jobs that are currently running or jobs that are queued. You can also see the history of jobs. That's a new feature. So you can see what was recently solved. You can see what API was running, whether it was solved to optimality, or it was interrupted, or it was determined to be infeasible. You can also get the log information from an old job, and they're also to see what parameters were used when a model was solved. So you've got some history information from that compute server. And finally, the administrator could do some nice things to see what licenses are available in the cluster, to kill jobs that are running. Now, these are not things that the individual would do. This is something that the administrator could do, and also update the configuration on the fly. So that's very nice. While you have the configuration file to make things persistent, you can also update the configuration on the fly by the administrator commands, and you could do that without having to restart anything. So that keeps the systems up and running. In this example, we're updating the job limit on one of our servers to allow up to 4 solves to happen concurrently. So there's no license limit on the Gurobi compute servers, but for performance reasons, you might want to limit the number of jobs. And so you can see that in the first command on the bottom, we increased the job limit to 4. And then the second command, we queried that limit. And now you see at the bottom that server 1 gets a job limit under the JL column of 4, but the second server, server number 2, still has the default job limit of 2. So that works great. But what if you're in a situation where you don't have a server available right now, you can't go out and buy one, or if you need a server sometimes, you only need it for just a few days, or you need it for a few hours each month? Or what if you need to get multiple servers in multiple data centers because you want to get a high amount of reliability, and your data center, is only one location? If there's any kinds of failure of your data center, that might cause a bad impact for your application. The perfect solution for that is Gurobi Cloud. Now, Gurobi Cloud is just putting the Gurobi compute server onto the cloud. Gurobi is the leader with optimization on the cloud. We were the first optimization provider with enterprise-grade optimization on the cloud. It's something we've been doing for almost 9 years now. And the nice thing about the Gurobi Cloud product is that we support all Gurobi interfaces and all platforms. So you can work with a Mac, Windows, Linux. You can mix them all together and use those to connect to the Gurobi Cloud. It's built with security and using industry standard HTTPS encryption, as well as we isolate each tenant. So if you're running as a cloud customer, you're using a computer that's dedicated to you, and that computer isn't used by any other Gurobi customers. So you're not competing with them for the processor, for memory, and certainly there's no data sharing. So it has a nice amount of security just built in. Also, running on the cloud requires no changes to your code. So anything you would do with Gurobi, you could also do on the cloud. So let's take a look at this, and let's do a quick demonstration of Gurobi Instant Cloud. So to do this, I'm going to open up the cloud administration website, and it's cloud.gurobi.com. And there's a nice little welcome page, but I'm going to click on the button that's going to open the Instant Cloud Manager. And that gives me some information. Now, as a Gurobi employee, I actually have 3 different licenses. Most users would just have 1 license assigned to you. And what I want to do is I want to tell my client computer that I am going to connect to the Gurobi Cloud. And to do that, I'm going to use a new license key file. So I'm going to use this license name number 178672. And so I will download the license key file corresponding to that. So just click the little download button. And now, I don't want to replace my ordinary license key file. So I'm going to set an environment variable so I could use my cloud license key file. So let me do that. I'll set that license key variable file. And now let me try to solve that same model I did earlier, that integer program. So I'll solve it. Now I don't need to give any special parameters because I'm using the license key file that corresponds to my cloud license. So I start it. Now, of course, I'm waiting for a server to boot. I'm getting that dedicated server, so it's going to take a couple of minutes for that server to boot. And so you see a few things happening. Here at the bottom of my screen, it gives me the text that says waiting for cloud server to start. So it's starting that server for me. And if I look in the other window on the web page, you can see that it's giving some progress information indicating that a server is starting for me. This usually takes about 2 to 3 minutes for that server to start. Once it started, I could reuse it and I don't have to wait. But that first time I'm going to use it, it's going to take a couple of moments for it to start. In a few moments, I'll tell you some other ways you can start that server that I don't have to wait. Now it's done. It's already booted, which is great. And it solved my same model. But it was a slight difference in that output. This time, it told me it's got a job, just like we saw earlier. There's some capacity on my pool, but it says now that's an encrypted connection. So our cloud configuration is built with encryption by default. So it's got that nice encrypted connection, and it solved the model. So if I want to solve a different model, let's say I want to solve that linear programming model, I could solve that model, and now it's very fast. I'm not waiting that time for the server to solve. If, say, I want to use the interactive shell, it will also work with the cloud. So it took a brief moment to create the connection. It says a job ID, there was capacity, and it started the encryption connection. So anything I would want to do in interactive mode with Python, I could say create a model, create some variables, and create my 3 variables. I could add a constraint. And I could solve the model. Not a very interesting model, but it solves and does that all on the cloud. So I can quit, and I've stopped that. But let's take a look at what happened on my server. So right now, I could look at the jobs and I actually see there were 3 jobs that solved on my server. There was 1 MIP, 1 by Simplex, and the last one, the most recent one, was also by Simplex. I can look at some of the information, like for my MIP model, I could see the log information from my model. So I can look back at this history information using a web page, and it says that it was solved to optimality in the top left. It tells me about the model. It was a very simple model, and it told me what were the parameters for my compute server and some plot of the objective function. We'll take a look at that a little bit later. But some nice information I can view on the web, as well as, of course, on my client-side computer. So all of this is done, and I don't really have to worry about a whole lot of things. It's all done and managed for me automatically. So I'm going to leave that run in the background while I go and return to our presentation. So the Instant Cloud has an additional part beyond the Gurobi compute server, and that's the part to manage your computers. So when I started solving, it managed that automatically because I told my client computer that I gave it a different license key file. It would automatically start my cloud servers for me. So there was an automated provisioning that told the cloud manager to start my servers. That's when I had that brief waiting period of about 1 to 2 minutes. Once the server started, that server was dedicated to me, and then the client could be used to connect to that server and do whatever kind of optimization computation that I wanted. This allows me to seamlessly offload optimization jobs to the cloud, and allows me to do things like solve challenging models. Like, let's say I want a machine with a lot more processors or a lot more memory, I could do that on the cloud. I can also use this if I have spikes in demand. Again, if I have certain times of the month where I need to solve a lot more models, I could have some licenses that I have in my own computing facilities, and then I can get some additional computers and additional Gurobi licenses for those few hours out of the month. Also, if I've got periodic optimization needs, if I need it only for a few weeks out of the year or for a short-term project, I could get the computers just for when I need it. If I'm building a cloud application, of course, I might want to have the rest of my optimization parts on the cloud, so I could use Gurobi Cloud, as well as have failover to have these multiple data centers. Now here I only ran 1 computer, but if I wanted to run multiple computers, it would allow me to run those multiple computers, and it will automatically put them in different data centers, so that way I've got a higher degree of reliability. So the Instant Cloud Manager is the web interface to manage your different cloud computers. So this is specific to Gurobi Cloud to allow me to start and stop computers. You saw that I had downloaded the license file, and something I didn't do, but I'll do it a little later, I could customize that compute server's configuration. For example, I could tell it what region I want it to run in. We have multiple regions in North America. We have computers that are available in Europe, as well as in the Asia Pacific region. You can also just choose what kind of computers that you want to get, including computers with lots and lots of cores and lots of memory. You can also choose how many compute servers that you want to run. And the Instant Cloud interface lets me monitor the machines and the jobs. Now, these are features we've had for a while. Let's talk about some of the new things that we introduced in version 8. First of all, we added a secure HTTPS protocol throughout. So again, that gives an easier integration with corporate firewalls and proxies. There's no custom port to worry about, and the protocol is based on web standards. So it uses standard security and standard data encryption. If you could browse a web page in your company computers, you can use Gurobi Cloud. So the same standard protocols, which was a problem for our customers using the older version. Also, the cloud has better robustness to handle intermittent network issues. If you're working on a computer that has Wi-Fi, loading a web page works because it'll retry and get all the different components of that web page if there's any kind of internet or any kind of Wi-Fi interference or some kind of unreliable internet connection. And we're using those same technologies to power Gurobi Instant Cloud, and Gurobi Compute Server. So that way, if there's any kind of momentary internet connectivity problem, your optimization model will still solve. Another new feature is this job list and job history information. So you can see what happened with the main server worker jobs, which we'll talk about in a few minutes, jobs that are queued and waiting for a compute server. You could also administer jobs by aborting jobs that are either running or waiting to be run. And you can also see that history to see what happened. Did that job solve to optimality? Did it fail? Was that job aborted for some reason? And you've got this nice job dashboard. Now, the models I solved were pretty simple, but here in this picture, you'll see some more complicated MIP models. And what's not solving one more complicated MIP model. And one thing I wasn't able to demonstrate because it would take a little bit longer is to show the conversion. So on the lower left-hand part of this window, you'll see the objective plot, and you see in blue on top the incumbent, the integer feasible solution, and in red below is the bound. And so you see as they're getting closer and closer, you're getting towards MIP convergence. And that shows you that in a nice graphical way, as well as the standard log in the lower right and some summary information. Now, I just showed the history of my current runs, but you could actually see prior runs and what happened. Was there any kind of network failure that took a little bit longer than the standard timeouts, as well as if jobs were stopped or aborted. So you get that full history, and you can see where the client was, which license it was used, what cluster it was connecting to, and it keeps that history over the last 90 days. This is an optional feature. If you don't want to use that, you can turn that on or off. Another new feature is the machine usage metric. So you can see if you've got multiple compute servers running, you can see what's the performance of that compute server. So here in this slide, you see one server is running and is running at 100% CPU, meaning that's very active, it's very busy. It's not using all the memory. That's good to see. That means that we've probably got the right compute server configuration for this application. And we've got a second compute server that's idle. Now, something I talked about earlier is what if you need to increase or decrease the number of compute servers because you've got lots of clients running, and now maybe afterwards those clients are done. You don't need those clients. You don't need as many compute servers. You want to stop paying for them. You can change the scaling of the number of compute servers that you're running up or down, and it will add the compute servers to the cluster or remove them automatically on the fly. And that's a very nice new feature. There, you don't have to reconfigure anything on the client. You don't have to stop the existing compute servers, and this all happens transparently. So if you add compute servers and you've got a large load of clients, as soon as those servers will boot, they'll start removing the jobs from the queue. So if you had a long queue and now you've got some new servers started, they'll start to take some of the load from the queue. If you need to scale down, it will not kill any existing jobs. Those jobs will finish. So those will finish, and then once the load is reduced, then those compute servers can be shut down, and you won't be paying for them. So far, I've shown you what this looks like from the web interface. What if you don't want to control things from a web interface? We've got you covered in that case as well, because we have a full RESTful API to manage anything you would need to on those machines. So first, you could manage the cluster. You could change the configuration of that cluster as well as see its current configuration. And if you need to get down to the machine level, you could do that as well. So the cluster is the group of machines, and you've got a RESTful API giving you the create, retrieve, update, and delete commands. And on the node, the individual machines, we have the same kind of commands to tell you, what's the current configuration, what are the jobs for the individual machines and the jobs for the cluster. So you could manage this in any type of a programming language using a RESTful API. We also have tools to help you automate that, but you could use any programming language to access this RESTful API. So that lets you manage the machine and cluster level. You can also manage the jobs. So you can list the jobs, return the current job, get the log for those jobs. Anything you would want to do with the jobs has a second form of a RESTful API to manage those jobs. And you can also monitor and manage the jobs for the pool scaling. So one of the great uses of Gurobi Cloud is to do parallel and distributed optimization. So let's get away from the cloud technologies and compute server technologies and just talk for a few moments in general about the optimization algorithms. And to do so, I'm going to talk about the technologies for parallel and distributed. So on the left-hand side, we'll talk about parallel computation. At Gurobi, when we talk about parallel computation, we mean one computer that has one or more processor cores and one or more processor sockets. This is something that Gurobi has done throughout our history. We have parallel MIP branch and cut, we have a parallel barrier algorithm, and we have concurrent optimization. This is something you would do on one computer, such as a laptop or a server in your data center. Distributed computation, in our terminology, this is when you're using multiple computers that are linked together via a network. This is a newer feature for Gurobi. And in fact, not only do you have these multiple computers, but each of these computers have multiple processing cores, and they could do parallel computation. So you've got two kinds of parallelization. You've got parallel computation that can happen on a single computer, and then you've got the parallel computation that happens on the multiple computers. So when you're working with multiple computers together, you have to think about how can you keep those computers doing useful work as efficiently as possible. You have to think about the computer architecture. So here's a little picture of the computer architecture, a little diagram of that. And so this box represents a single computer, and this single computer has multiple processor cores. Now it has, computation it's going to do on its own with its own memory, but then it also has, it has the link between the multiple computers. And when you think about what it can do, it has a very fast processing communications inside of that computer. The communications from one computer to another, it's fairly fast, but it's nowhere near as fast as the communications that's inside of the computer. And when you're building the optimization algorithms that are going to be shared and distributed among multiple computers, you have to think about that network between it. That network from one computer to another is like 1,000 times slower than the fast communication that's available inside of the computer. So we want to build some algorithms that are going to keep the cores busy with useful work, as well as keeping the independent computers doing some useful work, but managing that communications bottleneck that happens from one computer to another. So we have three kinds of distributed algorithms that we provide from Gurobi: distributed tuning, distributed concurrent, and distributed MIP. Distributed tuning is probably the easiest to understand. When you're doing parameter tuning and you're trying to test different parameters, you could test them on similar computers. So this is something that we do in Gurobi support. Gurobi customers give us test models and say, hey, what's the best, fastest, most effective parameter for our model? If you have multiple computers, you can have those multiple computers testing different strategies. For example, the MIP focus parameter, there are different values, like the default value of 0, MIP focus 1, which is working on finding feasible solutions, and MIP focus 3, which is working hard to work on the bound. You could try those different parameters on different computers and find out which one's the most effective for your model. And this is something that Gurobi support does all the time. This is a perfect application for distributed algorithms because those solves are completely independent. We're not going to talk about that in a lot of detail because that's just something that you do in development phase. We're going to talk in a lot more detail about distributed concurrent and distributed MIP. Concurrent is multiple independent solves of a single model using different strategies. And distributed MIP is going to take the MIP search tree and distribute that among multiple computers. So let's talk about that in more detail. Let's start with concurrent optimization. So the idea of concurrent optimization is to run different algorithms or strategies on different machines or different cores. And the first one that finishes is declared the winner, and that's the one that we get the solution, and we use that solution. Well, these are completely independent solves, and they're nearly ideal for distributed optimization. Again, we're taking a single model, we want to run it on different computers, and we're going to use those different parameters and see if one of them is going to lead to faster solve time. So we're going to send a copy of the model to each machine, give it slightly different parameters, and find which one gives us the fastest solution, and use that and return that back. So if we're going to apply this to LP, we could try different algorithms like primal simplex on one computer, dual simplex on a second computer, and barrier on a third computer. For MIP, there's a lot more options for different strategies, like the MIP focus parameter or different cutting plane strategies. But the simplest and the easiest one to do is to vary the seed that's used to break ties. So in MIP, there's a lot of times you've got different decisions to make and a bunch of different options that look nearly identical. For example, let's suppose I have 3 fractional variables, each equal to 0.5, and they're supposed to be integer valued. So I've got a branching decision on these 3 different variables. Which variable do I want to branch on right now? I could try one on one computer, a second on the second computer, and a third on the third computer to break that tie. And after I branch on that, maybe one of them is going to lead to a much faster solution. And that's in fact the built-in default strategy with concurrent MIP. But you can also customize this if you like. You can actually pick the exact parameters that you want to use on the different computers. So let's look at the performance of concurrent MIP, and let's look at some performance based on the MIPLib 2010 benchmark suite. So this is a standard set of mixed integer programming models that are used for different performance testing. So if it's better than 1.0, that's going to mean that concurrent MIP is faster. So the default would be 1.0 is the running of MIP on one computer. So in the first table, let's look at the performance on 4 computers versus 1 computer. So the models that take 1 second or longer are easier models. And these models, of these models, we have some that win, but some that are slower. But we do get some speed up, and that speed up is about 1.26 times faster. In the larger and harder models that take 100 seconds or more, we have a lot more winners, and we have a bigger speed up. Now that's in 4 computers versus 1. If we increase the number of computers and use 16 computers and compare that versus 1, we get an even bigger speed up. The models that are 1 second or longer, we get an average speed up of 1.4x, so a little bit of a speed up. But what's nice is the harder models get quite a bit faster. The speed up goes from 1.5 when we had 4 computers and increases to 2.0 when we have 16 computers. Let's talk for just a brief minute about what the difference between the easy and the simple models versus the harder models. When we have the simpler models, we do have a lot of them that lose. They get slower when we run concurrent MIP. And there's a kind of a natural explanation for that because concurrent MIP has some overhead. You have to tell each of these independent computers to get a copy of the model, so there's some communication time, and then there's some additional communication that takes place during the optimization algorithm. It's pretty small, but that's to say, hey, are you the winner? Have you solved? Which one is solved first? And so what you would expect is, in fact, what happens is that the easier models, some of them benefit, but fewer of them benefit than the harder models. And in fact, that extra overhead sometimes hurts the easier models, but very seldom hurts the harder models. So one of the takeaways from this is that if you've got an easy model, concurrent, distributed MIP, and parallel algorithms aren't going to benefit you nearly as much as the harder models will benefit. So what if you don't want to use the default strategy? You can use a custom strategy for concurrent MIP. So for example, what if I want to try different and actually that's not just for MIP, that's also true for LP, but it tends to be used more often for MIP. let's say I want to try two different computers with very different parameters. So instead of just using those tie-breaking parameters, let's say I want to give one computer a parameter of aggressive cuts and the second computer a parameter with aggressive heuristics. So I could do this in just a few lines of code. I create two different concurrent environments. I'm going to call them 0 and 1, concurrent environment 0 and concurrent environment 1. On environment 0, I give it the aggressive cuts parameter of cuts equals 2, and on environment 1, I give it the aggressive heuristics of 0.2. I then call optimize and then discard concurrent environments. So this example shows you the code for Java, but you could do this in all of the Gurobi programming interfaces that are object-oriented and the C programming interface. So you could do this in C#, in C++, in Python, etc. So concurrent MIP is pretty simple. Let's get to something a little bit more complicated and quite a bit more powerful. Let's talk about distributed MIP. So distributed MIP is a manager-worker idea. We have a manager that's going to send a copy of the model to each worker, and it's going to be tracking the progress, the status of the different workers. So it'll be looking at the dual bound and the worker node counts, and it's going to try to rebalance the search tree. We've got the MIP search tree, and we're trying to put useful work on the different workers. We don't want those workers to be idle, but we don't want them to be doing. We want them to be doing some useful work. And when there are new incumbents, that incumbent information is very useful for bound information, for cutoff information on the different workers. So when a new incumbent, a better incumbent's found, it needs to communicate that to the different workers. So the job of the workers are going to be to solve the MIP nodes for their subtrees and report the status and feasible solution. So this is like the idea of parallel MIP, but taking that to multiple computers. And we need to synchronize that periodically and make that deterministic. So there's two parts for the distributed MIP. We have a ramp-up phase, an initialization phase, and the main phase. And that's very important because to have the workers do useful work of exploring different parts of the MIP tree, we actually have to have an initial tree. So how do we create that initial tree? We go back to that idea of distributed concurrent MIP. We have, in the initial ramp-up phase, we give each worker, each computer, a copy of the model and tell it, solve it with different tie-breaking strategies. And we let that run for a while to create that initial tree, and we let each worker do some work exploring it with different tie-breaking strategies. And once we've gotten a large enough tree and we pick the best tree among those workers, that's going to be the winner. And we then take that tree and distribute that to the multiple workers. We throw out the other trees and we say, this is our tree that we're going to use, and distribute that tree and use it among the different workers. So then in the second phase, the main phase, we take that tree, we break it up in different pieces. We then collect the nodes from the winner and put the different pieces on the different workers. And of course, we're going to periodically synchronize and rebalance. So let's take a look at performance. And one of the key questions is, are you better off using one big computer or a bunch of smaller computers? So let's take a look at that. So here's a diagram of one big computer that has 16 cores. And on this big computer, those 16 cores might be on multiple processor sockets. This would be like a very powerful server. And let's compare the performance of that one big computer with distributed MIP on 4 independent computers. And these aren't 4 big servers. These are 4 smaller computers. And in this case, each of these smaller computers will each have 4 cores. So we're going to compare 16 cores, but compare the performance of one server with one large server with 16 cores and 4 smaller independent computers that are linked together with distributed MIP. And the question is, what's the benefit of a big computer as compared to 4 small independent computers? And let's take a look at that. We're going to return to that MIPLib 2010 library and use those models to compare the performance. And so in the first row of this table, you see the performance of our 16-core machine. And in our 16-core machine, we get a speed up for the simple models of 1.57 times. And when we compare that with the 4 core machines, the 4 smaller computers, those get a speed up, but it's a little smaller. It's 1.43. It's close, but it's a little smaller. But here's the interesting part. On the larger and harder models, those models that take 100 seconds or more, we get a bigger speed up for those models as compared to the smaller, easier models. But what's really interesting is our 4 independent computers, it gives a very comparable speed up. It actually is slightly faster than our 1 large server. So that's very useful information. First, it says that we didn't give up a lot of performance when we designed this distributed MIP to be very smart and give us do some very smart strategies, even though we have that communications bottleneck. We don't have the same fast communications like we do inside of that 1 big server. While it's a little odd, you say, well, why is that? Why are those 4 independent computers actually a little bit faster than the large server? And the reason is that smaller computers tend to have a faster clock speed than the large servers with a large number of processors. And so we could benefit from that when we work with those 4 independent computers. So of course, though, the big server has a benefit on the smaller models because we have less overhead than we do with that communications bottleneck for the smaller models. So in fact, this is very good news for the distributed MIP algorithm. The distributed MIP algorithm is doing some very intelligent things, and it gives some very good speedups. Even on the smaller models, while it's a little slower, it's not far behind. And for the big models, it really is just as good as that big server. But there are pros and cons. You know, the 4 independent computers tend to be cheaper than 1 large server, so they're cheaper from a hardware standpoint, but there's more work. When you have 4 independent computers, especially if they are in your own data center, there's a lot more administrative work. You have to apply patches to them. You have to configure them. You have to, just buy the computers in the first place and plug them into the network. They all need power. They need communications. There's more administrative work in dealing with 4 independent computers. The good news is on the cloud, that administrative work is much easier. So we'll talk about that in a few minutes. So let's look at the distributed MIP as we increase the number of computers. Again, we'll use that MIPLib 2010 benchmark set, and we're going to compare that against 1 computer. So 1.0 means the performance on 1 computer, and let's compare that versus independent computers. So we get a small speed up when we go to 2 computers. That speed up gets much bigger when we go to 4. And again, that speed up is much better for the larger and harder models than for the smaller and easier ones. When we go to 4 to 8, we're starting to get a little bit of benefit. The benefit for the small and easy models is getting to be not much benefit. So we doubled the computer from 4 to 8, and the benefit for the small and easy models goes from 1.43 to 1.53. Not much of a benefit. But for the harder models, they still get a nice benefit. They go from 2.09 times speed up to 2.87, so quite a bit faster. But when we double it again, going from 8 to 16, now the speed up for both the small models and the larger and harder models is not that big. So there's kind of a sweet spot of 4 or 8 computers. Somewhere in that range tends to be a sweet spot for distributed computing. Once you get beyond that, the additional computers, they give you a benefit, but it's not that big. And again, it's far under a linear speed up. 4 computers, even for the larger and harder models, it's not giving us a 4 times speed up on average. It's about a 2 times speed up. And when we go to 8, it's nowhere near an 8 times speed up. We get a nice speed up where it's a little bit, even for the harder models, it's a little bit below 3 times speed up. So we get a nice speed up, but it is always going to be far below a linear speed up. Now, there are a few models that get a huge improvement in going to distributed MIP. So in the Seymour model, which is a hard set covering model from the MIPLib problem, if we were running that model on 1 single computer, we get a solve time that's a little bit under 3 hours. If we increase the number of computers from 1 to 16, our solve time reduces a lot. So it's not linear. It's not 16 times speed up, but it's really good. We get a 9.1 times speed up, and we went from almost 3 hours down to it's about 18 minutes or so. And if we double that and go from 16 to 32 computers, it's not quite a 2 times reduction in speed, but it's a pretty big reduction. We now get from 18 minutes down to a little over 10 minutes, and that's great. We've got a model. We've taken 32 computers, and we took something that took almost 3 hours, and we reduced it to just over 10 minutes. It's not linear, but boy, that's a really great speed up. But what characterizes this model to give us a good speed up It has a large search tree that's a very balanced search tree. So we're giving that search tree to multiple compute nodes. We're able to give each of them a pretty useful search tree to explore. It's well balanced. It looks very bushy. And this picture gives you an image of one such search tree. Many models do not benefit from distributed MIP. If it's an easy problem, you're using too much machinery, and in fact, those models will often be slower with distributed MIP because of the additional overhead. So if it's a model that is particularly easy, maybe it has, it's optimal immediately, there's no benefit. If the search tree is small, if it solves at or near the root, there's not many opportunities to exploit parallelism, both on a single computer and with distributed MIP. So that's not going to benefit from multiple computers. Also, if the search tree is unbalanced, like in this picture where we're doing mostly a dive on the left-hand side, then there's not going to be much of a search tree to send to the different compute nodes. So let's compare the distributed concurrent algorithms with the distributed MIP. So with distributed concurrent, that was that simple idea of giving the tie-breaking strategies, and let's use this more advanced strategy of distributing the actual MIP search tree to multiple computers. And in fact, this time your intuition is correct, because the harder, more intelligent strategy of distributed MIP is giving a much bigger speed up, both for the simple models and for the harder models. So the simple models in the upper table and the harder models in the lower table, going from concurrent to distributed. The more intelligent distributed strategy gives up a much bigger speed up for both the easy and hard models. So how do you do distributed optimization via the cloud? You do that in 3 easy steps. Step 1, you configure your cloud pool to use your distributed workers. Step 2, you start solving your model. And step 3, there is no step 3. It actually is just 2 simple steps. So let me give you a nice demonstration of this. Let's go back to my computers and let me configure a new pool. And so in my new pool, I'm going to create a pool that's going to have multiple computers. So we'll do this, we'll call this the webinar pool. We're going to use my license that I was using before. And this time I want to give it 3 compute workers. And since I'm located in the western part of the US, I'm going to use a compute center in the western part of the US. And let's give it some nice, powerful computers. Let's get 4 powerful computers, and let me download the license key file for this new option. So this time I'm going to run 2 new windows. First, let me create 1 new window, and I want to do a comparison. I'm going to do, first I want to use that new license key file. And so now I'm going to solve I have to find the file. There we go. So I'm going to solve the model in 2 windows. So in my lower right window, I'm going to use my multiple computers with distributed MIP. And in my upper left window, I'm going to do the same thing with my single computer that I had earlier. So my single computer was already booted. So it's already going to start the optimization algorithms. So I'm not waiting for that single computer to boot. So it's already out there and solving it. I had booted it earlier for the earlier demonstration. But you can see on the web page, it's waiting for those 3 workers and that 1 compute server to run. So it's launching that new computer, that new pool of 4 computers to do my distributed MIP algorithms. So on my upper left, it's still working. It's solving that model on the 1 computer that I had booted before. Hopefully my new computers will be booting pretty soon. They're booted. So it's the client should start any moment now, connecting to them. Looks like they're booted, and now it's solving. So the output's slightly different because I have my my compute server on my left, but I have my pool of 4 machines doing my distributed MIP. You can see that in the output here. It says distributed MIP count 4, and it has multiple workers. So it has one, a master and 3 additional workers. And give it just a few more moments. It should solve the same model from, this is a particular test model from MIPLib 2010. And remember, I didn't have, the first machine started independently. It was already, there was no booting time for the first computer. And wow, my compute server cluster, where I have my 4 computers, is done already. It has an optimal solution after 41 seconds, and including the boot time, it's finished before my original computer has even returned its optimal solution. So it still has, after it's almost 2 minutes of runtime, and it still has a MIP gap. It's not finished yet. And my multiple computers in my distributed MIP cluster, my cluster of computers for distributed MIP is already done. Now my single computer is finished. It took over 2 minutes. My cluster finished almost 3 times faster. And it was really easy. I just had to do a few clicks and I got my cluster available to run. So the different pieces are available. They fit together. There's the Gurobi optimizer. That's something you've probably been working with for a long time. Those are the optimization algorithms. We then make those available with client-server computing over the network with Gurobi remote services. The next piece of the puzzle is Gurobi Cloud for Amazon Web Services that runs the Gurobi remote services, these client-server computing on Amazon Web Services, a public cloud system. And then Gurobi Instant Cloud is that nice interface to control and operate those machines. The distributed algorithms are an integral part of the product. They're built on top of Gurobi Compute Server, and there's no special binary involved. I didn't have to recompile my application, and it works with all Gurobi interfaces. It'll even work with existing applications. You don't need to modify your application to do distributed algorithms. So as we improve our MIP solver, it will also make the distributed algorithms faster. So some reasons to use the cloud for optimization. You pay for just what you use. If you need it for a short-term project or for some occasional use, there's no hardware or software to purchase or configure. You can get that computing power in just a few minutes. And it also makes it very, very easy to get distributed optimization algorithms. You also get increased robustness by having the ability to run multiple computers in multiple locations. And the cloud computing environment, these are world-class computing centers. They're really held to the highest standard. But there's lots of people that still use traditional Gurobi licenses. In many cases, it's cheaper to own or rent. If you're running an application 24 hours, 7 days a week, it's more cost effective to just buy the Gurobi licenses than to be paying for them hour by hour. In a few applications, if there's a particularly large models that are easy to solve, then those models, the data transmission could be a bottleneck because you're sending information from your computers over the public internet to the cloud. In a few cases, some customers are not ready to trust computers on the internet, though that's changing more and more over time. And in fact, all of the compute server algorithms and the distributed algorithms I've demonstrated today, you could run them both on cloud and on premises, meaning in your own computing infrastructure. So everything I demonstrated today, if you want, you could run that on your own computing infrastructure. The cloud is not required. All the same technologies are available. The only exception is the cloud management interface, because we provide our own nice interface to control the computers. If you're going to run them in your own computing infrastructure, then you're going to have your IT team managing the starting and stopping and administration of those computers.